So there's a new homework assignment up on MU Online. It's not very difficult. I think you'll appreciate the fact that as we're moving into some of these later chapters, we've kind of gotten over most of the really intense, crazy stuff. And from here to the end of the semester, the material is a little bit easier. Okay, so hopefully that's that you find that to be true. That doesn't mean that you should slack off. Yes?
Is our final going to be on what we're covering now, or will it be everything?
The final will be primarily from what we cover between now and the end of the semester, but everything is fair game.
Right.
So it'll be maybe 60 or 70% of what we do from now to the end, and then a couple of problems just to make sure you still know and understand how to do the other stuff. Okay, so today we're in chapter 14, and we're talking about humidity, essentially. So a lot of what we're doing from chapter 14 is talking about the way that you can specify what the air is like. So we talked about temperature before, like when we're looking at the temperature of an ideal gas, we can associate that with a specific volume, we can associate that with an enthalpy. But now as we're moving into this chapter where we talk about human comfort and air conditioning, we also have to determine how much moisture is in the air. Because air is not just simply a gas on its own, there are other things in it. And so we have to consider that when we design any kind of a system where we're taking into account human comfort. So we're going to talk about the different states, how to find them, and the different techniques that we'll use in order to find some of the different terms and terminology. So there is a lot of definition in this chapter. There are a lot of definitions in this chapter, so I behoove you to write them down and make sure you understand the difference between, for example, specific and relative humidity, or dry air and humid air, or that one's an easy one. But there's a lot of terminology in here that you should pay attention to, and I've tried to bold it everywhere it comes in the lesson. So when we're talking about just air in the atmosphere, we refer to it as atmospheric air. And if it doesn't contain any water vapor, we call it dry air. But even in the middle of the desert, there's usually some dissolved moisture in the air. That it's very rare to encounter dry air unless you're specifically filtering it so that there is no humidity in it at all. And as I mentioned, the amount of the water vapor in the air plays a significant role in human comfort, which you should understand living here in West Virginia, that the summers, 80 degrees when it's a relatively dry day is very pleasant, but 80 degrees when it's 95% humidity is not very pleasant at all. So when we analyze these systems, similar to what we did in the last chapter, we have to look at this combination of air and water vapor and sort of find a way to lump it together so that we can analyze it as one fluid. Rather than looking at the air individually, looking at the water individually, we can analyze it together. And one way that we do that is we make certain assumptions about the temperatures that we're operating at and the state of air with water in it at those temperatures. Okay, so if we want to find the enthalpy of dry air, it's just C sub P times the temperature. Or if we want to find the change in enthalpy of dry air, it's just C sub P times the change in temperature. And this is kind of an interesting analysis in this chapter, because when we calculate this C sub P times the temperature, this is like the one and only case that we actually use Celsius rather than Kelvin. Because the way that the equations are designed throughout this chapter is using 0 degrees Celsius as a reference point. So take note of that when you're calculating the enthalpy of dry air, it's based on the reference point of 0 Celsius rather than absolute 0. And so we're using just Celsius or Fahrenheit when we're making those calculations. And that's because meteorologists and people who are working in determining humidity in the air often work in regular units rather than thermodynamic units. Okay, so if we look at a TS diagram of water vapor, we can see that everything on this side of the dome is a vapor. And we notice something that at below 50 degrees Celsius, these constant enthalpy lines intersect the saturated vapor line. Okay, that tells us that enthalpy is approximately constant at those temperatures, that it's not varying, it's not changing. We also know that for an ideal gas, enthalpy is approximately constant with temperature. So we are going to make an assumption in this section that when we're calculating the enthalpy of a water vapor, we're going to treat it as an ideal gas. Okay? So this atmospheric air, which is a mixture of regular dry air plus some humidity or some water vapor that's in a somewhat gaseous state, we're going to assume that it's behaving much like an ideal gas. Which means that we can make similar assumptions as we did in the previous chapter, that the pressure of the air plus the pressure of that water vapor gives us our total pressure. So if we're looking at atmospheric pressure, which is 101.325 kilopascals, something like that, then it's a sum of this dry air pressure plus the pressure from our vapor. And we'll see how we use this in a minute. So if we want to calculate the enthalpy of a water vapor at a low pressure and a moderately low temperature, it's approximately equal to the enthalpy of the saturated vapor at that same temperature. So this is similar to the compressed liquid approximation, but in this case we're just looking at this side of the dome rather than the other side of the dome. So again, this is only applicable at low temperatures and low pressures. It doesn't work if we are operating high up in the superheated zone. That doesn't hold true any longer. So we can calculate the H sub G two different ways. We can look at the tables, or we can actually use these formulas to figure it out. And we can do the example. We're going to look up H sub G at 0, 10, and 50 degrees Celsius for water, and then we're actually going to calculate those same values and see how close they are. So if we look in the table, what is H sub G at 0 Celsius? And our table doesn't go to 0, it goes to like 0.01 or something, but we can approximate it at 0. What is it at 0?
So 2500.9.
Okay, so 2500.9, so we can very easily see that 2500.9 plus 1.82 times 0 is going to be equal to 2500.9. So at 0 degrees Celsius, we get a 0% error when using the equation versus looking it up in the table. Okay, so what is the enthalpy at 10 degrees Celsius?
2519.2.
So 2519.2. So we can put that in the equation, 2500.9 plus 1.82 times 10 is equal to 2519.1 kilojoules per kilogram. So that gives us an error of about 0.004%. What about at 50 degrees C?
So 2591.3.
Okay, so 2591.3. So again, 2500.9 plus 1.82 times 50 is equal to 2591.9. So that gives us a percent error of about 0.02%. Right, that's already been multiplied by 100. So you can see that it is a pretty good approximation that we can use this equation to calculate, or we can look up the values in the property table and use the H sub G value with very little error in making that assumption. Okay, so now we're going to start talking about humidity. And when we talk about the total amount of water vapor in the air, we're talking about the specific humidity. So this specific humidity, which is has the symbol of a lowercase omega, is the mass of the water vapor divided by the mass of the air. So the units are kilograms per kilogram, but it's not unitless because it's kilograms of water vapor per kilograms of dry air, that's an actual unit. you can't cancel kilograms out. An alternate way of determining it, because we've said that this acts as an ideal gas, is we can use the ideal gas law. And we see that our temperature cancels out because the temperature of the water vapor and the temperature of the air are the same temperature. And our volume cancels out because we're assuming they're occupying the same state. So we're just given P sub V over P sub A, R sub V over R sub A. So if we take R sub V, which is the R value for water vapor, and divide it by the R value for air, we get this number, 0.622. So this 0.622 PV over PA is an alternate way of calculating our specific humidity. So if we know the partial pressure of the water vapor and the partial pressure of the air, we can use that instead. Or if we know the mass of the vapor and the mass of the air, we can use that to figure out the ratio of the partial pressures. So another way to write this, because P sub A is equal to P minus P sub V, is we can write it all in terms of the water vapor pressure and the pressure of the atmosphere. Okay, so specific humidity, again, is the total amount of water vapor that's in the air relative to the amount of air. This value does not change with temperature. It's a set value. Dry air has no water vapor, so omega is equal to 0. But as we add water vapor to the air, it reaches a point where the air cannot hold any more water vapor, and so we refer to that as saturation. So there's so much moisture in the air that in order to add any more moisture, something else has to condense. Or if you decrease the temperature of the air by any amount, then some of the water will condense out of it. So it's referred to as saturated air at that point, and the amount of the water vapor in the saturated air at any specific temperature and pressure can be determined from this relationship. So the mass of the water vapor in the air is equal to the total mass of the air times this 0.622, which is the ratio of R values, multiplied by P sub G. And P sub G is equal to P sat at T. Okay? Oh, it says it right below that. So this P sub G value will be looked up in this in these property tables. So if you know you're at 20 degrees Celsius, you would go to your table A4, you would look up the temperature 20 degrees Celsius, and you would find that your saturation pressure is 2.3392. So the pressure of the water vapor in the air at that temperature, because it's a vapor, because it's been vaporized, is 2.3392. Okay. Now we talk a lot about feel in thermodynamics, like it feels hot, but that's not necessarily a very good way of determining temperature. It's also the same for humidity, that it can feel very humid even when it's not that humid, or it can feel more humid even when, or it can feel less humid or more humid depending on temperature. So it's dependent upon the amount of moisture that the air holds relative to the maximum it can hold. So if you're at a very high humidity at a high temperature, your air can hold even more humidity, so it may feel less humid than if you're at a lower temperature and you're reaching the maximum amount of liquid that your air can hold. So as your specific humidity is constant, your temperature changes and your relative humidity will change in the same manner. So if the temperature is increasing, your relative humidity decreases, and if your temperature is decreasing, your relative humidity will increase until you reach a saturation point. So this relative humidity is the mass of the vapor divided by the total amount of mass that the air can hold at that temperature. So this M sub G is not the same thing as the mass of, so in our this equation is the mass of the air in the denominator. Here is the mass that would be represented by the total amount of water that the air can hold at that temperature. And the way that we find that is just this ratio of P sub V over P sub G. alternate way of looking at it. Okay, so when you have 100% relative humidity, it means that your air is holding the maximum amount of water that it can hold at that temperature. And if you have 50% relative humidity, it means you're halfway there. Okay, so with relative humidity, it changes with temperature, but specific humidity does not change with temperature. Okay, so some alternate expressions that they can be related one to another, the specific and the relative humidity. So again, these all go back to that ratio of R values, and we're looking at the pressures. So this 0 to 1 or 100% humidity is, again, dependent upon temperature. And this is the value that they quote on weather channels, right? So this relative humidity that they're giving you is relative to the max that it can hold. Okay, so now when we're looking at enthalpy of atmospheric air, it's a combination of dry air and this moisture that's in the air. So there's going to be some amount of dry air, let's say there's 1 kilogram of dry air, where the amount of moisture in the air is related to the specific humidity. Okay, so this W term, which is the ratio of the mass of the vapor divided by the mass of the air. So when we want to calculate our total humidity, our total enthalpy, which is an H, we can do the mass of the air times the enthalpy of the air plus the mass of the vapor times the enthalpy of the vapor. Or if we divide through by the mass of the air, it can be rewritten as the enthalpy of the air plus this specific humidity multiplied times the enthalpy of the vapor. And the enthalpy of the air is approximately equal to the enthalpy of the air plus this specific humidity times the enthalpy of a saturated vapor. Because if you remember, these enthalpy lines are approximately constant. So whether we take the enthalpy here or here, it's going to be approximately the same. So the enthalpy of the vapor can be taken to be the enthalpy of a saturated vapor at that temperature. Does that make sense? Okay, so that simplifies analysis because we only have to look at it at the temperature. We don't need to worry about the pressure necessarily. We can just find it there. So let's use this in an example and try to see how to calculate some of these values. This is your exam, by the way, again. Okay, so we have a tank that has 15 kilograms of dry air and 0.17 kilograms of water vapor at 30 Celsius and 100 kilopascals total pressure. Determine the specific humidity, the relative humidity, and the volume of the tank. Okay, so the first thing we need to do is go to our table, and we want to look at 30 degrees Celsius and get a couple of values there. So the first one is the saturation pressure at 30 degrees Celsius, and what is that value?
4.2469 kilopascals.
Okay, 4.2469 kilopascals. Okay. So the first thing, the specific humidity, what's the Greek symbol for specific humidity?
It's the omega.
Omega. And what's it equal to?
Mass of the air over, like mass of the vapor over mass of the air.
Yeah, mass of the vapor over mass of the air, which is equal to 0.17 kilograms divided by 15 kilograms. And again, remember, this is not unitless because it's kilograms of water over kilograms of dry air. So we find omega in this case, or the specific humidity, to be 0.0113 kilograms of H2O divided by kilograms of dry air. Okay, that's pretty easy. So part B, the relative humidity, what's the symbol for that?
Pi.
Okay, so this is equal to omega times the pressure divided by 0.622 plus omega times P sub G. What's P sub G in this case?
So a piece of
Okay, so this is P sub G. So if we plug in the numbers for that using 100 kilopascals for the total pressure, and this omega value is what we determined previously, P sub G comes from here, then we find this to be 0.4214 or 42.14% relative humidity. Okay, so then for the volume, we can calculate it two different ways. We presume that the volume of the air and the volume of the water vapor are the same. So if we treat either as an ideal gas, we can say that the volume of the air is m times the r of the air times T over the pressure of the air. It's 15 kilograms is the mass. The R value is 0.2870 kilojoules per kilogram Kelvin. Our T value is 303 Kelvin. This is still the ideal gas law, so we do have to use Kelvin in that equation. But what is the pressure of our air? Okay, 100 kilopascals is the total pressure. But the total pressure is equal to the pressure of the air plus the pressure of the vapor. So the pressure of our air is going to be equal to P minus P sub V. What is P sub V? What's the pressure of the vapor?
P sub G.
Okay, it's almost equal to P sub G. P sub V is actually equal to this times P sub G. Okay, so the relative humidity multiplied by the pressure if it were a saturated vapor. Okay, so we find P sub V is equal to 1.789 kilopascals. So our P sub A, which is P minus P sub V, ends up being 98.21 kilopascals. So that's what we use here, 98.21 kilopascals. And we find that the volume is equal to 13.28 meters cubed. Okay, now note that I said that you can find it two ways. The second would be, instead of using the volume, calculating the volume of the air, if we want to calculate the volume of the vapor, it's m times the r of the vapor times T of the vapor over the pressure of the vapor. So in this case, the mass is equal to 0.17 kilograms. The R value for water vapor is 0.4615 kilojoules per kilogram Kelvin. The temperature is the same, 303 Kelvin. But now our P sub V is this value that we calculated earlier, 1.789 kilopascals. So if we do the math on that, we find 13.28 meters cubed is our volume. So they are equivalent, because they occupy the same space. Any questions on this example? Do you understand the difference between the pressure of saturated vapor versus the pressure of our actual vapor? Okay, so it's based on the relative humidity of it. All right. Moving on. You may have noticed when you wake up in the morning that even if it hasn't rained, the grass will be wet, right? And what is this called? Dew. So excess moisture in the air condenses and it forms dew. And the reason that this happens is because the temperature decreases overnight, and so the capacity of the air to hold moisture also decreases. So let's just say it could hold 100 kilograms of water all around your house, wherever, and the temperature decreases. Maybe now it can only hold 99 kilograms of water, and so one of those has to end up on the grass because it condenses out. Because the capacity of air to hold water is higher at higher temperatures, and at lower temperatures it has to condense out. So this relative humidity will increase as the temperature decreases. And once it gets to 100%, any additional decrease in the temperature results in water condensing out from the air. So it ends up on the ground or on the grass or on the cars or whatever else is outside. And the dew point temperature is the temperature at which condensation begins when the air is cooled at a constant pressure. So if we look here, what temperature is that going to occur at? The saturation temperature, right? So if we're cooling at a constant pressure, then we end up right back there on that line on the dome. So our dew point temperature is the saturation temperature at whatever pressure we're operating at. That's when it will start condensing from our liquid. So we can determine whether or not some moisture will condense out of the air based on determining the dew point temperature. So if we calculate a dew point temperature and whatever object we're working with is higher than that temperature, no moisture will condense on the outside of it. But if it's lower than the dew point temperature, moisture will condense. So we need to determine with this can of soda if it will sweat in a room at 70 Fahrenheit and 38% relative humidity. So the can of soda itself, the surface temperature is 40 degrees Fahrenheit. What we want to see is if the dew point temperature is greater than or less than 40 degrees Fahrenheit. So that will tell us whether or not liquid will condense on the outside of that can. Okay, so we're given 38% relative humidity. What is that Greek symbol? Phi. E5, so is 0.38. That means our vapor pressure is equal to phi times P sub G. What is P sub G at 70 Fahrenheit?
.3633 psi. Right?
0.3634 psia. Okay, so that tells us our P sub G, and then we multiply it by the relative humidity to figure out the vapor pressure of our water, which is 0.1381 psia. Then we take that value and we go back to the table and we try to find the saturation temperature at P sub V, okay, or this pressure that we've calculated, which is equal to 0.1381 psia. So the saturation temperature by interpolation is 43.17 degrees Fahrenheit. So our saturation temperature is higher than the can of soda. Does that mean that dew will condense or dew will not condense?
It will, because we're below the saturation temperature.
Yeah, we're below the saturation temperature. So 40 degrees Fahrenheit. I always want to write a C. Ugh. 40 degrees Fahrenheit is less than the dew point temperature, so it will condense. If we calculated some value that was below 40 degrees Fahrenheit, then the can of soda is not cold enough to have liquid condense on the outside of it. Yes?
So since it will condense, then it will sweat?
Yeah. Yeah, so the can will sweat. Condense, sweat, same kind of thing, right? The can's not actually sweating, it's just collecting moisture from the outside. So sometimes you are not actually sweating, sometimes you're collecting moisture from the outside too, right? Okay. Any questions on this? All right. So again, the distinction between P sub V and P sub G. That P sub G is some fixed value at the temperature. But this partial pressure is based on the relative humidity. So it's a combination of factors that determine whether or not something will happen, right? So if this humidity, instead of being 38%, were 20%, that would change our pressure, right? So it would be, instead of 0.36334 times 38, it would be times 20. So instead we'd have a pressure of 0.0727 kilopascals. And if we were to go to the table and look up the temperature at 0.0727 kilopascals, I'm just going to eyeball it, I'm not going to calculate it. Fahrenheit. It looks like our dew point temperature would be below freezing, so the liquid would not condense on the outside of the can. Okay, so it's a combination of factors that determines it. The temperature of the can, the humidity in the room, the temperature of the room, all of those factors play a part. Okay, adiabatic saturation. This is a methodology for helping us determine relative humidity in a space. So this is called an adiabatic saturator. And basically what we do is, without adding any heat to a system, we're blowing air through this channel. And by so doing, because of the motion and because of convective forces, some of that liquid water will evaporate and will join the other water that's in the air. And if this tube is long enough, or if this chamber is long enough, when it exits here, it will have 100% relative humidity. That means that it's holding all of the water that it possibly can hold without some of it condensing out. Okay, so this adiabatic saturation chamber allows us to determine the adiabatic saturation temperature, which is the temperature at which the saturator picks up all of the moisture that it can, and that's the exit temperature of the system. Because as this air is blowing through here and it's absorbing water, the temperature is also decreasing. So let's just see how we figure this out. So in this adiabatic saturation chamber, we can do a mass balance on the air. And we see that the mass flow rate of the air coming in is equal to the mass flow rate of the air going out, but that doesn't change. And it's just equal to the mass flow rate of the air. So that airflow is constant. All the air that comes in has to leave. The mass flow rate of the water coming in here at state 2 is equal to the mass flow rate of the water plus, that's coming in with the air, plus whatever's evaporated into it. Okay, so this flow of the water out is equal to the flow of the water in with the air, because it's absorbing, plus there's some that's being evaporated and being added to this of the water. Does that make sense? All right, so then we can rewrite this. We can say that the mass flow rate of the air times omega 1 plus the mass flow rate of the fluid is equal to the mass flow rate of the air times omega 2. Because omega is equal to mv over ma, or m dot v over m dot a. So we've taken this equation and rearranged it and substituted in omega so that we only have the mass flow rate of the air to worry about. So the mass flow rate of the fluid, or the evaporation of the fluid, is equal to the mass flow rate of the air times the difference in relative humidity from the outlet to the inlet. So that's how much air is being, or how much moisture is being absorbed by the air, or picked up by the air as it goes through. Okay, so we can also do an energy balance on this system, where we can say the mass flow rate of the air times H1 coming in plus the mass flow rate of the fluid times the enthalpy of the fluid is equal to the mass flow rate of the air times the enthalpy of the air as it leaves. We can replace this with C sub P T1 plus omega 1 times Hg1. So that's the enthalpy of the air plus the enthalpy of the moisture in the air, plus omega 2 minus omega 1 times HF2 is equal to C sub P T2 plus omega 2 Hg2. Okay, now if we combine terms and rearrange, we have this C sub P times T2 minus T1 plus omega 2 times H sub F 2 minus H sub G2 plus omega 1 times H sub G1 minus, H sub F1 minus H sub, sorry, hold on. Omega 1 times H sub F2 minus H sub G1 is equal to 0. So then if we rearrange and solve for omega, we get this result. Here. So C sub P times T2 minus T1 plus omega 2 times HFG, which is H. H sub G minus H sub F over HG1 minus H. That should be in F2. I believe. Let me double check that. Yeah, it's an HF2, so I need to fix that in the slides. And then omega 2 from before is this value as given. Okay, so an adiabatic saturation chamber is a way of determining relative humidity, and we'll do some examples that are similar in a minute. So a similar concept is that instead of passing our air through a chamber and having it pick up moisture along the way, we can take a thermometer, and if we just use the thermometer in the air like normal, and we'll do a demo of this in the next class period. So if we just measure the temperature of the air, right now it's like 21 degrees Celsius in this room. If I were to put a liquid wick or cotton or gauze or something on the end of this, and then either blow a fan on it or wave it around, the temperature is going to decrease because some of, and we're assuming that the water is the same temperature as the room air. It's not measuring the temperature of the water. But once we start blowing air across it, some of that water will be evaporating, which will be removing heat from the thermometer, and that allows us to determine something called a wet bulb temperature. The difference between the wet bulb temperature and the dry bulb temperature helps us determine how much humidity is in the air. Because if there's a lot of humidity in the air, it's not going to evaporate from this wick very quickly. But if it's very dry air, it has more of an ability to pick up moisture. Okay, so we'll look at some of the calculations involved with that allow us to determine the relative humidity using the difference between a dry thermometer and a wet bulb thermometer. Okay, so this wick can be submersed in liquid water so that you can have a continual reading, or you can just do a quick and dirty easy one and get the temperature once it's stabilized. And so this wet bulb temperature and the dry bulb temperature, as I mentioned, are used to determine humidity. And there are some devices, like one is called a sling psychrometer, which you'll have a wet bulb thermometer and a dry bulb thermometer at the same time, and you just swing it around and you measure the temperature of both simultaneously. And we use it to calculate humidity in a similar way to the equations from the adiabatic saturation process. So let's look at that example. We have a room with a dry bulb temperature of 26 Celsius and a wet bulb temperature of 21 Celsius. The fact that the wet bulb temperature and the dry bulb temperature are different means that this is not 100% humidity in the room. If those were exactly the same, then the room would have 100% humidity and we wouldn't need to calculate anything. So assuming a pressure of 100 kilopascals, we want to determine the specific humidity, the relative humidity, and the dew point temperature. Okay, so what is the equation again for specific humidity?
So MV over MA.
Okay, it's MV over MA. Are we given any information about the mass in this problem? No. So we need to go back to the equations that we used for the adiabatic separator, where we look at the relative humidity based on the temperature of the wet bulb, and then we substitute that back into the equation for the relative humidity using the temperature of the dry bulb. And so we'll go through that process. First, let's look up a few things. So we know that we're at 26 degrees Celsius. What is our saturation pressure at that point? And these have to interpolate, so I'll just write them down. I hate examples that do that, but whatever. Okay. So our saturation pressure is about 3.38522 kilopascals. And then we're also going, and this is equal to PG1. Okay, P sub G1. We're also going to need H sub G1, which is 2548.32 kilojoules per kilogram. Dry air. And H sub F2, we don't need that. Okay. So then we look up PG2, which is our wet bulb temperature, or pressure at our wet bulb temperature, which is 21 degrees Celsius. So PSAT is equal to 2.5348 kilopascals. HF2 is 88.098 kilojoules per kilogram. And HFG2 is equal to 2451.14 kilojoules per kilogram. Okay, so those values are all interpolated off the table at 21 Celsius and 26 Celsius. So now our omega-2 is equal to 0.622 P sub G2 over P minus P sub G2. So this tells us the relative humidity of the wet bulb thermometer, which is 0.01618 kilograms of H2O divided by kilograms of dry air. Then we find omega-1 is equal to C sub P times T2 minus T1 plus omega-2 times HFG2. And these equations, again, were developed in the previous slide over Hg1 minus H sub F2. So we looked up all these values. We have Hg1, we have HF2, we know omega-2, we already calculated it, we have HFG2. T2 is this 21 degrees Celsius, and T1 is the 26 degrees Celsius. So this is T2, this one is T1. So if we put in all the numbers for that, then we find that our specific humidity for this process, or for this room, is 0.014 kilograms of H2O per kilograms of dry air. So now we find phi, which is omega-1 times P2 divided by 0.622 plus omega-1 times PG1. So again, PG1 is the saturation pressure at 26 Celsius. So if we put in those numbers, we find our relative humidity is 65%. Then to calculate the dew point temperature, we need to find the saturation temperature at PV1. So PV1 is equal to PG1 multiplied by the relative humidity. So that's 65% multiplied by 3.38522 kilopascals. So we find that PV1 is equal to 2.2004 kilopascals. And then when we look up our saturation temperature at that point, it's 18.93 degrees Celsius. So that's our dew point temperature. And the dew point temperature should always be, unless you're at 100% humidity, your dew point temperature will always be less than your room temperature, and usually less than your wet bulb temperature as well. Okay, any questions on that example? They're fairly easy problems to do, but it's also really easy to put in the wrong thing. So be very careful about your pressures and understanding the difference between a piece of G and a piece of V, and then make careful note when you're looking up enthalpy values that you get the right one. So HFG on the table is HG minus HF, right? And it has its own column. And then make sure you look up H sub G1 and H sub F2, that you have to get the right values in there. So it's not that difficult to do, but it's easy to mess it up if you have the wrong things. Yes?
So with like 100% humidity, would that be like water's on the walls and stuff?
Yeah. I mean, have you ever been running your air conditioner or whatever, and it's like there's moisture inside your house, or when it's really, really humid outside, a lot of times it doesn't take much for that moisture to condense. And in many cases, 100% humidity means that it's just about to rain. It starts condensing out of the sky. Yes?
I know when you were saying that, it reminded me when we went on vacation to Mexico, they basically can't use wallpaper down there because the humidity is so high all the time, it'll just eat it off the walls.
Just peels it up. And they probably don't have really great air conditioning either. Because an air conditioning system, part of what it does is cool your air, but it also removes moisture from the air to increase comfort. Which is why sometimes when you run your furnace constantly during the winter time, there's not very much moisture in the air anyway, and it becomes very dry air. If you wake up with like really dry eyes and sore throat, a lot of that is because your HVAC system is removing moisture from the air. So sometimes running a humidifier is beneficial. Whereas if you have a basement that's always kind of damp, you might run a dehumidifier so that you remove that moisture out of the air. So it contributes to human comfort, it contributes to like the lifespan of indoor surfaces in a building, whether or not you have mold. If you've got mold issues in your house, it's usually because your humidity is too high. So we deal with that a lot more here than out west. And people further south deal with that even more. My brother-in-law lives in Miami, and it's just always wet there everywhere all the time, just because it's so humid. Okay. So there's 3 different ways that we talked about today for determining the relative humidity. Using the dew point temperature can be used to determine the vapor pressure, and in turn you use that to calculate the relative humidity. So it's a very simple way to do it, but it's not always practical if you don't already know a dew point pressure or a dew point temperature. And then the adiabatic saturation device can be used by measuring the difference between the inlet and the outlet. You can find the relative humidity of the inlet. But it's not really practical to have that device set up to use. A wet bulb thermometer is also an easy way to do it, where you could actually do those measurements and calculations fairly easily at home, and we'll do an example of that next time. It's simple and practical, but there are also many devices on the market now that are electronic that use capacitance to tell how much humidity is in the air, and that's a fairly easy way to do it. So knowing how to do it if you were in the field and you needed to know the humidity for certain calculations, you could just put a cotton ball on a thermometer and swing it around if you had to, if you were in a MacGyver situation or something like that. So again, be very careful with your calculations and using the correct numbers in these. It's easy to get confused and think, okay, well the soda can is 40. Is that the temperature I look up in order to find the dew point, or what do I need to do? So just follow the examples. Everything is scanned. There's a couple of additional examples in the text, and you could probably do your homework in under 2 hours. I did it fairly quickly today after I wrote it, so it shouldn't take very long at all. And thanks for participating in Halloween. And Patrick, be looking in your email for an Amazon gift card. Good job. So most everybody gets 10. Chris, I think, was a little like,
I made mine like 10 minutes. I honestly forgot about it.
so, you know, you put a lot of extra effort into it.
A for effort.
You kind of just take the picture to your shirt.
Yeah, how does that go in? Does that go in like you got a, what?
So like your quiz points will be out of 40, and then you'll just get an extra 10 points. So you could potentially get like 50 out of 40, so then it increases.
Okay. So if we're logging it, it would be out of 0?
Well, it'll be out of 0.01 because it doesn't let me do anything out of 0 on that. It doesn't know how to calculate that. So, yeah. But I don't use MU Online for figuring out final grade. I have a spreadsheet for doing that. I can leave that column at 0.
It's made it